Let's let's take a brief look at what we mean by models. I know many of you will be familiar with it, but this course may be watched by biogeochemists, biologists, social scientists, I hope. So they need to be introduced to the concepts. So Earth is a sphere. It has land, it has ocean, it has vegetation, it has mountains, it has glaciers, and so on. Weather and climate models have typically relied on just representing the mountains, land, ocean, taking the energy coming in and computing the energy going out along with the processes that happen inside, like evaporation, condensation that releases energy, that drives the weather and climate, and more sophisticated ones have started to add, we will see the timelines, carbon dioxide, dust, which affects processes like scattering light, cloud processes, droplet sizes in rain, and so on. And water vapor is of course needed because it's a critical part of the whole process of condensing, forming clouds, moving energy in the atmosphere, etc. So these are what we mean by grid sizes. So you can see that the Earth will be split into a number of grids, and if the grid is 500 by 500, you can imagine that a cloud is going to be 500 kilometer scale, or they have to find a way of putting clouds only a fraction of the grid. It gets complicated and so on and so forth. And representing mountains, which are very sharp edged rising features, will also be difficult. You have if you have grid boxes of 500 kilometers and so on. So there are many processes like cloud formation, going from molecules of water vapor to condensing on so-called cloud condensation nuclei, and coalescing into clouds by collisions, and so on. And within the cloud you have to have water vapor, ice, graupel, etc. Obviously happen at small scales, and if you have very coarse model, then you cannot resolve many of the small scales. Okay, so we have to be careful about those things. And here is how the ocean would look, and you can see if you have very coarse resolution, then the continental shelf and so on will look very discrete, like a step instead of this continuous line we should have, right? But that's what you have to deal with. But increasing the grid size is not so difficult, but then running it on a computer, if you have instead of, let's say, 10,000 grids, if you have 100,000 or a million, the computing time begins to grow up very quickly and becomes impossible. For example, if you want to make a weather forecast start at 6 a.m. and you want to forecast for 8 a.m. or 10 a.m., then you want the model to be run quickly. And if it takes a very long time, then you won't be able to make the forecast. And the same thing for climate projections and so on, where you will need to make many realizations, or paleoclimate, where you have to run for centuries, maybe. Okay. So models evolved this way in terms of their history. I think I showed one version of this before. Mid 1960s, atmosphere and land surface were being modeled already in GFDL, and ocean was being modeled as well. Suki Manabe, Kirk Bryan, and all the other big names from there have played a tremendous role in setting these up. 70s and 80s, we added vegetation, we added sea ice. By the 90s, there was aerosols in the atmosphere and solar forcing, as well as volcanic aerosols, and now you have carbon cycle, various dynamic vegetation should come in here somewhere, and especially in this century, They've also added the land ice sheets, which are very critical now for making realistic projections, especially considering that Greenland is melting so fast and Antarctica has a very complicated situation with the ocean and the ozone hole creating special situation, as well as some parts glaciers could be growing, in some parts the glaciers are melting, and so on. So you have interactive vegetation, carbon and nitrogen cycle as well, and so on. Okay, so these tools are now supremely complicated, and paleoclimate modeling wants to use these to do simulations either of time periods, like just do last glacial maximum. So you will do a simulation of just focused on, let's say, year 21,000. Okay, so you just take your forcing, you run the model to reproduce the conditions at that time, or you make these so-called transient simulations where it's actually going from year 0 to year 2000. It's a simulation year, not real year. It's a model year. Okay, basically that means model can be run from any time to any time, and it takes radiation as an annual cycle. It has its own daily cycle as well, and you just have model years. They don't correspond to the real years. Okay, so here the Nordic Sea's meridional overturning being simulated with a freshwater flux being put in. Why? If you remember your global conveyor belt, deep water formation in the North Atlantic requires warm temperatures, high evaporation, salinity being left behind to produce heavy waters. But if you put fresh water, then you are going to damp the freshwater deep water formation. So you can see the dip that's going to happen in the overturning circulation in Sverdrups, which is 1 million cubic meters per second of water. Okay, so in this case the idea is to look for how quickly the system recovers after it's been perturbed. Right, we will see examples of such perturbations that happened around 8,250 years ago and during the Younger Dryas, as we mentioned before. So you can see that recovery happens after 100 years and so on. These are different cases of the simulation, which I won't go into, but I just wanted to introduce the idea that this is trying to simulate the 8.2 kilo year before present event as the thermohaline circulation in the model. Okay, so just to conclude that thought, this is the kind of options you will get in models. Energy budget models are very simple, and they just look at the energy coming in, energy going out, and see what kind of diffusion of energy, for example, is needed to move the energy from the low latitudes to high latitudes. They're very simple. We know that energy is not just being diffused, it's being advected, and there is convection processes and so on. There are system models with intermediate complexity. There are atmosphere, ocean, general circulation models, and Earth system models. And this paper argues that you can make a choice on resolution in space and time, time scale to be simulated, transient or pieces of the past climate, number of processes you want to include, dynamic coupling between ocean, atmosphere, atmosphere land, atmosphere glaciers, and replicates, number of cases you want to make, uncertainty assessment in the system you want to make, and so on. So enabling and performing fluid navigation of this model space to identify a suitable balance of details will be a key part of this new approach they are imagining. They call it variable detail model, or VDM. So it's like having a toolbox which allows you to make a choice of which process you want to explore, what time scale, what spatial scale, and so on, which is very useful but not always easy to manage. There are many now pedagogical tool set up by Marcus Jochum at the Niels Bohr Institute in Copenhagen, Denmark University, or whatever it's called, and atmospheric model set in Stockholm by Rodriguez, I think. They are written in Python, so anybody can go in, download them. You get a few knobs you can tweak and run the model to see the sensitivity. Okay, so if you put fresh water in the North Atlantic, in the Greenland, Iceland, Norwegian Sea, how the overturning circulation changes. If you perturb it, how long it takes to recover, and so on. So it's one thing to do simple models for pedagogical purposes, teaching purposes, but it is a whole different game when you actually want to do projections. For projections, you need realistic Earth system models which capture the most critical feedbacks. And the first to the fifth assessment, most models actually didn't have land ice models, so they were represented in some simple way to estimate sea level rise and so on. So now more and more models are going, including land ice sheets, for example. So as we go forward in time, the sophistication and hopefully the accuracy of the models will continue to get better.